Alright, so we started with the essence of process control, and then we said we have to actually model the process so that we'll be able to control it, right? And then we said when we model this system or these processes, we end up getting differential equations, right? And then the order of the differential equation tells us the type of process that we are dealing with, right? So as we looked at this, for instance, the continuously stirred tank reactor is a first order process, right? Or a first order system, right? And then that will mean that it will be described by a first order differential equation. So it could be something of this sort. Let's see. We have okay, have like this. Then the dy dx, right? So clearly, first order system, right, or first order differential equation. This is under constant, and we have this, and then we have and then we're going to talk about what each of these 10 mean, right? So if we are talking about a process, mean that there will be a particular input and there will be a particular output, right? So definitely this y t is time. This y is the output function, all right? What we'll be getting at the end of the result, end of the process. So if you are looking at a particular target, that will be the y, right? And then these a1, a1, and then a0 are constant, right? Fine. And then the b is also another constant. And then this ft is what we call the forcing function. Basically, is the input that we're giving to the system. So one of the inputs, or the simplest one we can give a system, is what we call a step change, right? So let's say a system, let's do a graph. Let's say something like this, right? So let's say this is a temperature, right? Let's say degrees Celsius. And then this is time, right? Just a second. If let's say the system is operating at temperature, right? Particular temperature like this, then suddenly there's a sudden change in temperature, right? So something like this. At this particular time, there's a sudden change in temperature. Temperature rises, right? Abruptly, and it moves to a new temperature. So this is, let's say, T1, but then abruptly within a short period it changes to T2, right? So this is what we call a step change. There are different types of changes, but this particular one is what we call a step change, right? Fine. And there's the common one that we generally be using at the discussion that we are doing here. So yeah, so this is the first order system, right? Yeah, there are different orders, right? So you look at something like this. Basically, when there's a way for you to rearrange it, and we've talked about the transfer function, right? Where it compares is the ratio of the output to the input, right? So generally, when we rearrange this one in such a way that we have, let's say, dy dt, right? Dy dt, and then we end up getting, let's say, y alone, which is the output, right? So that would mean that we have a1 here, a0 here, and then we have this to be b on what, a0, right? And then we have the forcing function. When we have it this way, then we can clearly see the output, we can clearly see the input, right? So when we get it this way, we see that whatever is attached to the differential equation here is what we call the, let's see, no, whatever we have attached here is what we call the time constant. So if you have any differential equation, first order, and you're able to rearrange it to this form, then this one here, this a1, this a naught, is what we call the time constant, right, of the process. Remember, time constant of the process, and we will talk about why we specify or put that p there when we are moving on, right? And then this b on a is what we call the gain, right? And we'll talk about this very soon. Fine. So that will mean that what we are talking about to be the transfer function, which we said is generally the ratio of the output to the ratio of the input. So let's see, generally output is y, right, in Laplace domain. So S here means Laplace domain, and then input, let's say u, right? So this is the transfer function. So for the first order system, the transfer function usually have this form, right? So let's see, where here we have the gain, so this gain of process, and then we have the time constant for the process, and then we have s, and then we have 1, right? So this is for what we call a first order system, right? But then there's another form for first order systems where, before that, let's come to this. When you look at this diagram, what do you think is happening? A continuously stirred tank reactor. You can see that it basically has the ability to hold mass, right? And then it can also hold energy, right? Because of this thing. So E is equal to, oh, sorry. Right, so if it can store mass, right, then it can definitely store energy, right? So any any system that can store mass or energy is a first order system, right? But then there's another thing. If the system, right, if the system has the ability to control the outflow or has resistance to outflow, then it's a, what do you call it? It's what we call a first order lag system, right? So there are two. We have first order, let me write it this way. First order lag system. And then we have what we call a pure, it's also a first order, but we call it a purely integrative system, or let's say capacitive process, right? And then for these two, though they are both first order systems, there's a slight difference in how the transfer function appears. So for the first order lag system, to be like this, what we just wrote initially, right? So the transfer function will be this, of this form, the time constant of this, of the process plus one, but this one here will just be time constant of the process, otherwise just s, right? So this is for purely integrated systems. But most of the discussion that we'll be doing here will be but if there's a change, you see, will be for first order lag system, right? Yeah, and as we've discussed, most systems, because for the purely integrative or capacitive systems, they usually don't turn stable, right? But for the first order lag systems, they kind of like become stable after some period. But we want the stability to be fast, so that's why we did a control for these ones, and that's why we're seeing this one, right? Fine. So keep this structure in mind, the transfer function of the first order lag system, right? Fine. Okay. So we know what these first order systems are, and then we know how their transfer function appear. This is for first order lag system, and this is for what we call a purely capacitive or purely integrative system, right? Fine. And then we say that when we have system like this, right, whenever there's a change, or for instance a step change, right, which is what the simplest that we can apply, the system responds in a particular way, right? And this response can be traced, right? So generally, it says that whenever you, let's see, uh, whenever you have a system, a first order system, and then there's a change in the input, the system responds in a particular way. And then, as we've said, any particular system has a differential equation that describes it, and as such, it will have a particular transfer function that describes it, right? And the studies have been done already, and I said that if a system is operating, for it to be able to reach about, let's say, 63 point, and there's a graph for this, right? 63.2, yeah, it's a mistake. For it to be able to reach about 63.2% of its final value, it just needs this time, right? And oh, let's go over this. So the time constant here we are seeing is that whenever the system is happening and there's a change in the input, there's a particular time that it will take for the system to become stable again, right? And here we are talking about in the case where we've not applied a control system or a control mechanism to the system. The system itself, because it's self-stabilizing, as we said, we are not talking about this one, right? Because on its own, it's not on its own, it doesn't stabilize, right? Without external influence, right? But we are talking about this, so let's take this out. Fine. So for this one, for instance, for it to be able to return to, whenever there's a change in the input, it will take this time, which is what we call the time constant, for it to return to a stable state on its own, no control system applied, right? Fine. So that's what we call the time constant, this here. So before we come to this, let's talk about this. So this is the time constant, right? Time constant. And it has the same unit as time. Fine. And then this Kp, or the gain here we are seeing, is that whenever there's a change in the input, the system corresponds and then have an effect on the output as well. So this Kp here generally is something like this, is the same as the change in the output, right? All over, so that's why we call it a gain, all over the change in the input, right? So that means that whenever so this simplifies to be something like this, where we have the change in input. So let's make it u, right, as we've written initially. So let's just make it change in u times this Kp time what do you call it, gain of the process will be equal to the change in the output, which is y, right? So this means that whenever there's a change in the input, right? The system has its own gain, which is this. It multiplies it by that change in the input and has equivalent effect on the output that will happen, right? So that's what this gain talk about. The process, yeah, the steady state gain of the process is about, right? Fine. And then we are seeing that for first order system, right? Whenever there's a change or whenever there's a change in the input or there's a disturbance, right? There are certain time that it will take for it to stabilize, right? So let's see. Uh, okay. And then because the process that happens on its own, so let's see. Let's talk about this. So and these have been done already. These are works done, and then these are values that have been proven, right? So and then it's 63.2, and then we have 86.5, yes, and then we have 95%, and then we have what we call we have 98%, right? So what this says is that whenever the system is occurring, there's a particular time that it to take for it to reach its final value, and as we know, this system here what is self what stabilizing, right? So meaning it's predictable, right? Yeah, self-stabilizing meaning it's predictable. So if the process is occurring and then we know what the time constant is, which is this one right here, right? Which is this here, right? And we know what it's about. When a system is occurring, for it to get to about 63.2% of its final value, and this final value we can find it using what the final value theorem, which we've talked about, right? For it to get to about 63.2% of its final value, you just need one time constant, right? Just one. And if it's about you want to get to for it to get to about 86.5% of its final output, you need two, and then so forth, and this you need three, and then here you need four, right? So that's what these are saying. Yeah. And these are things that actually describe a first order lag system, right?